Hello, good morning, good afternoon. This is Benjamin from the Eclipse Foundation. Welcome to our virtual IoT meetup. So today we are with Jared and Andy from Marvell Semiconductor, and we're going to have we always try to have cool demos and show you guys some interesting IoT technologies. And so today we're going to talk JavaScript, we're going to talk IoT, and I think Jared, Andy, you have some cool demos, so whenever you want to get started, the floor is all yours.
Great. Hey, well, it's great to be here, Benjamin. Thanks for having us. We're broadcasting live today from Canoma World Headquarters in Santa Clara. I'm Jared, and this is Andy. And I think we're just going to go ahead and switch over to our presentation and get started. So this presentation today is about hardware simulation for IoT using Canoma Create and the Canoma.js framework. So simulation is obviously an important part of doing IoT development because it makes it easier to isolate and find bugs in your software, to quickly test new features without the need for physical hardware, work in distributed teams where hardware isn't available for everyone, and numerous other reasons that I'm sure most of you are aware of. So there are different approaches to doing hardware simulation, but today we'll be talking about the API-based approach used by our framework, which focuses more on simulating the input and output data that your application is using, rather than on the hardware interfaces itself. So a little bit about us. I'm Jared, and I'm here with Andy. Both of us are engineers on the Canoma team at Marvell. I'm focused mostly on building the tools used to develop applications for the Canoma platform, namely Canoma Studio, which is our Eclipse-based IDE. Andy has done a lot of the product development and technical work for Canoma Create, among a number of other things here. So you can read more about us on the Meetup intro page if you like. And so I think a good place for us to start is going to be to talk about Canoma Create and Canoma.js and what our platform offers for doing IoT development. More than likely, many of you aren't familiar with Canoma yet, so that's okay, because we're going to talk a little bit about it now. So I'll turn it over to Andy at this point for a brief introduction to Canoma.
Excellent. I will go on camera here and say hi for a moment. So I'm Andy with the Canoma team, and the gist of our team here at Marvell Semiconductor is that we came from a very software-centric background. We came from a world of mobile app development and embedded development for kind of consumer electronic devices back in the mid-2000s into 2010, before we were acquired by Marvell. And now we're here in this lovely giant building, Marvell Semiconductor. And our goal in life is to kind of bring our software expertise into the hardware world, and in particular to bring some of our usability and kind of user-centered design expertise into the world of building amazing open source tools and products for the world to use to build their own amazing products. And so I'm going to walk you through Canoma Create real quick, which is our prototyping toolkit for helping build JavaScript-based consumer electronic devices, IoT devices, things that connect to other devices and go out into the world and you can actually interact with. So if I switch over here, you will see a Canoma Create right here, live in the flesh. And it's got a couple of just random kind of sensors plugged into it. And you'll see here that we have this user interface on Canoma Create. If you're kind of used to the Arduino Raspberry Pi world, this is somewhat unusual. This is a kind of different approach to presenting what a prototyping toolkit can do and what it looks like. And so this is all written in JavaScript. This is all written using Canoma.js, which is our open source JavaScript framework. You can go to GitHub and search Canoma, and you'll find us right there. And then, as Jared is going to talk for the rest of this presentation about kind of working without wires and what it means to run in a simulated environment, I'm going to show you very briefly what it means to work with wires so that you can see the comparison. So here I have plugged into the device just a tricolor LED right there and a basic 3-pin potentiometer. Just looks like that. And the idea in Canoma Create is that you can go into here, into this front pin setting thing, and you can say, all right, I want the leftmost pin to be voltage, plus power. I want the second pin to be analog input, and I want the third pin to be ground. And so that's setting up this potentiometer to just work like a potentiometer should. Say apply, we go back here. And then just to show you that the thing actually works, we have this app called Pin Explorer that lets you come in here and see what values are coming in on that analog pin. So if I turn my potentiometer here, you can see that the input graph is changing. So we can show that we're actually like really moving electrons around and able to change the analog voltage level just by using that. Same deal with this tricolor LED. So that's plugged into 3 PWM drivers on the back of the device. And if I go over here into Pin Explorer, I can go into PWM, and I can actually change individual PWM driver levels. So if I turn this all the way off, we can make it a lovely Canoma green just by kind of dialing in only the PWM pin that controls the green channel there. And so that's the idea of kind of how you actually work with Canoma Create in the real world. It's got these 16 pins on the front, and then on the back it's got another 50-pin header. And you're always kind of plugging in wires and putting things together and building real things with real components. But as we've alluded to in the title here, that's not always the right thing to do. And so I'm going to kick it back to Jared, and he's going to talk about working without wires.
Great, yes.
Excellent. Back to the presentation.
Back to the presentation.
There you go.
All right, so now that you've had a brief introduction to Canoma, let's dive in and look at how you write code in Canoma.js to interface with components connected to the I/O pins on the hardware itself. So on the slide, this is actually a picture of my daughter, and no, she's not being tortured. She's actually participating in a sleep study, but I love this picture because it reminds me of why simulation is a good idea. So imagine like the mess of having to prototype and test this piece of hardware without simulation. Probably not too fun for the people that are helping do that. But we have to start somewhere. So first I want to explain a bit how you write code for interfacing with hardware using Canoma.js, because that's important to understand. So the first step is to create a JavaScript module that will provide an interface for your application to your various hardware components, so LEDs, sensors, motors, etc. We call these modules BLLs, so it's short for blinking light library. They can obviously do more than blink a light. The BLL defines some basic metadata about the hardware used by the module and provides an API that can be called by the application using asynchronous messages. So let's switch over to Canoma Studio now and take a look at a BLL, which controls a simple LED on a digital output pin. So this is going to switch over. There we go. Okay, so this is Canoma Studio. It's the IDE. It's familiar to those of you using Eclipse because it's built with Eclipse. We have some projects that are preloaded in here, and so the first thing we want to do is look at our JavaScript BLL module for an LED. You can see that it doesn't do a whole lot. What we do is there's a little bit of configuration that tells us what type of pin it's using. In this case, it's digital, and the direction is going to be an output because we want to control the output LED. There's a bit of code in the application to initialize the BLL, and then the BLL functions in this case turn on and turn off or invoke through messages sent by the application to the BLL. So you can see in here we've got various functions that are defined. Configure is required by the BLL to basically initialize any of the I/O pins that you're using. We've defined 2 functions as part of our API here called turn on and turn off. They simply just write a value 1 for turn on or 0 for to turn off that output pin. And then we have a close function which basically shuts down that I/O pin. So very simple stuff here. So I'm going to talk now a little bit about how the application's invoking these messages. So we'll take a look here at our main application. I'm going to skip over some of the mechanics for doing this because just to stay on topic, but if you're interested in learning more about the programming with Canoma.js, we have a bunch of resources online on our website. We've got some documentation, tutorials, and sample code, etc. So you can check all that out. So what you're going to see here is just a little bit of initialization in the main script of the application. What it's doing, it's invoking an asynchronous message on the on our pins thread, and it's calling that configure method that you saw in the BLL, and it's configuring some of the attributes of that pin. So, for example, in this case, telling what pin number on the actual device that we're using. The application, when you run it, it basically displays a button on the screen that turns an LED on and off. And when that happens, it updates the state of the button and then actually calls those functions that we've implemented in our PLL. You can see the code here. It's just a couple lines of code to do that. So that said, let's actually just run this on the device so you can see what it's doing. Okay, great. So here we see the application has got a button. It says turn on right now. When I touch it, it's turning the LED on and off. So very simple application. But now what I'd like to do is show you how this is going to work with the simulators. So let's take a look at what happens when we run the application in the Canoma Create simulator rather than on the actual device. Do that here. I'm going to click run. Now you see the application running on the desktop. When the BLL is initialized, it registers a UI for the hardware. So that's this little widget over here. And that's a UI for the component that's being simulated. In this case, it's the digital output LED. And when I interact with the app in the simulator, and click on the on button, then the LED state changes in the UI. So that's the kind of the basic general idea of how we visualize the simulators in our software. And so in order to implement the simulated behavior for the LED, there's a bit of work that needs to be done. And this is how all hardware simulators work in our platform, where we implemented the BLL for controlling the state of the LED on the physical hardware. We also have to implement a second BLL for the simulated behavior. So these two BLLs, if I'll switch back to Studio here, the two BLLs are placed in their respective device and simulator folders in the application or in the library project. And as you see, they have the same name. The tools take care of selecting which module actually gets loaded at runtime based on the target environment that the application is being run in. So for example, when we run on the device, it loads the LED.js module from the device directory, and when we're running in the simulator, it loads the LED module from the simulator directory. Let's take a look real quick at the implementation of the simulator portion, the simulator BLL. So as you can see, there's a little bit of configuration that tells the software which UI components we want installed, and then we also see all the methods that are implemented in the API in our device BLL are also implemented in the simulator BLL. The difference here is that the simulator BLL, rather than actually invoking methods for the pins hardware, we are calling methods in the simulator. So in this case, we're telling the simulator to set its value to on or off. So it's a little bit different, but the nice thing about this is that focus on making easier to develop the applications using a variety of hardware components. We're not writing simulators that are specific to the hardware interfaces. And so, but this involves having implementations that are already abstracted into higher level APIs. And so let's see. So we have several various data-driven UIs that exist for simulators required for simple data types such as floats or booleans. and which can be configured as inputs or outputs. For many complex hardware components, such we have custom UIs that can easily be built. For example, maybe you're simulating GPS or thermal printer or camera. So these can also be simulated using this technique. So let's just take a quick look at a couple other examples. You can see a few of these. We have an analog graph here. So this will be a simulation of hooking in an analog component like the potentiometer that Andy showed. So first, let's actually just run this in the simulator.
So fair warning here, Jared, your computer is running a few seconds ahead or behind your voice here.
Okay, good.
So pace yourself there.
Okay, so while this is catching up, there we go. Hopefully you can all see this. So here we're actually simulating an input sensor, so an analog input. You can see what the application is doing. It's drawing a graph on the screen here to show the analog values. And then in the simulator UI, we're actually seeing the data that's being generated for that analog input. So that's one thing we do is the simulators for inputs can actually generate data. And we have a few various ways that you can tweak the data that's being generated. We have some UI here that lets you change the kind of the wave pattern for the UI. All right. We can also set it up so that we're setting it using a manual control. In this case, I'm just changing the value of that analog input. And so this is nice because it lets us basically program our application, see how it's going to respond to the various hardware components that we're connecting to it. Without having to worry about like the details of how that hardware is actually implemented, the interface, what interface it's using, or anything like that, because everything is abstracted at the API level.
Yeah, and so to be clear here, like the power of what we're doing here is that, at the application level, absolutely nothing changes. The application has no idea whether it is talking to the simulated thing sitting here on the desktop with the dials and the sliders and all of that, or if the application is talking to the actual physical hardware, the real potentiometer sitting with a voltage differential and an analog input pin. From the application's perspective, exactly the same thing. It actually gets abstracted at this lower level where the BLLs go one direction or the other based on whether we're running on the desktop or the hardware.
That's right. So let's actually, just to show, we'll run this on the hardware itself.
Uh-oh. That means I have to find that button again. There you go.
Okay, so just fun, you can see here this is the same application running. We have an analog light sensor here, which when I covered up, you can see the value changing for that analog input. And he's going to turn on the light and make that spike up.
Fancy.
So again, there's one thing that's nice is that there are really no surprises in how our application is going to behave when we run it on the device. The simulator running on the desktop is actually the same software, just built for the desktop computer as opposed to the Canoma Create. So we don't kind of have to worry about so many of the portability issues between two devices running the Canoma platform. So that's another nice advantage of this. Take a look at another example here, which uses a custom simulator. So a lot of times you're gonna come across components in your development that will either use a kind of a custom interface, like maybe it's a serial and I2 interface, or if it's an output, like in this case, I'm going to show a 7-segment display that uses a serial interface. The kind of nice power of our tools here is that we have the flexibility to create these custom UIs in the simulator. So I'm going to run this.
Since we accidentally stumbled in there, I'll tell you what we just showed there. We actually can, on the desktop simulator, run a number of different simulators. So Canoma.js runs on Android and iOS just as much as it runs on custom hardware. And so we also have built into the Eclipse-based IDE simulators for iOS and Android.
Right. So what this application does is it's displaying the time on our 7-segment LED display. It allows us to actually change the message that's on the display. I can do that by clicking on this button here. Hello. Click OK. And then our message scrolls across the display. You can also adjust the brightness. So again, this is giving us a good idea of how our application is going to behave when we actually connect the hardware. But we didn't need, we built this application completely without the hardware at first.
Saves on shipping costs, if nothing else. You can do the 5-day shipping instead of the 1-day shipping.
That's right.
Continue building your appliation.
Yeah, so the idea here is that there is going to be a continuing library of sensors that we are building and other people in the community are building, where you'll be able to download those libraries, which include the simulators, and build your applications for those particular sensors or modules in the software before you even decide to purchase the hardware itself, which is kind of nice. It lets you do a little bit more experimentation. You may want to test a couple of different components and see what the libraries are like before you commit to buying anything. You may have a distributed team of developers where you only have a certain amount of the hardware that you've kind of committed to buying, but you can have, say, some engineers working on parts of the application where they don't necessarily require the hardware, but they can still run and test to make sure that everything is working. Mm-hmm. So a lot of advantages here.
And of course, those simulators and the BLLs and everything are part of our open source repository on GitHub.
That's right.
So you're going to run that on the hardware?
Yeah, let's run it on the hardware, of course. So here we see the time displayed on the display. I'm going to enter our message. And of course, we're getting what we expect. So that's a custom output module that we were using. So let's take a look at, I think, one more example here. I'm going to show an example of some hardware that has a custom input interface, and those are also important to be able to simulate. So this is an I2C touch shield from SparkFun. Andy, you might be able to talk a little bit more about this particular component. This particular touchpad, I think it divides the. That's I think a capacitive touch.
Yeah, it's a cap touch 9-panel sort of deal that just lets you simulate large regions. So you don't get touches for individual pixels. You get touches for a quadrant of the screen.
Right. So in this case, we can simulate that by we've just created a button for each quadrant on the screen, and when you touch the button in the simulator, it's generating the same data that would be generated from the actual hardware itself when you're using this particular library. So one thing that's kind of nice about this is I've never even seen this particular module. I don't even know if we have one here in the office.
We do not.
Someone has built some support for it, and it looks like it may be interesting to me. Maybe I have an application where I think this may be useful for my project. So I can integrate this into my application and see if it's something that would work. Again, where I haven't committed to buying anything, I don't have to learn how to wire it up or anything like that. I'm just interfacing it using the higher level API and testing it in the simulator.
And this is a good example of one of these deals where we're looking at the simulator for this touch shield thing here. And looking at the simulator, I literally don't know how it works. Like this might be an I2C component, this might be a SPI component, this might be analog. No idea, couldn't tell you. But from the application's perspective, again, it just doesn't matter. Like that's abstracted away and it just sort of works. And then if we were to dig into the underlying details of the hardware BLL, then we would see, suddenly how it actually works.
Right, and this, of course, is, well, it's an I2C shield. We can actually take a look at some of the code. So we can see here, it's an initialization. It's writing some initialization data to the I2C bus. Again, all of this, whoever built the library understands what that particular protocol is for this component. I don't have to.
Thank God for that.
Yes. And again, taking a look at the simulator, it's going to be kind of a lot of the same. There's some behaviors for the interaction with the buttons in the simulator that's defined here, and then actually creating the button objects in the UI. So again, there's not a lot of code here. We have a lot of samples. If in Canoma Studio, you can access all of our samples that are in our open source GitHub repository directly from Canoma Studio. You can click on Install Examples. We've broken the examples out into categories of examples. So in the pins category, these are all of the kind of hardware-y kind of.
Let's show how to fire up the tricolor LED, since I already showed that guy.
Okay. So we're gonna.
It also has my favorite custom simulator in our entire repository.
Right. Tricolor LED.
PWM. Yeah.
This one.
Yes.
Okay. So this installs the application, PWM tricolor LED. Again, that's pulled directly from our GitHub repository. So if it's been updated or something, you're always pulling the latest version of that. Let's go ahead and fire this up. All right. Yes, again, so you can be as creative as you want when you're creating your own simulators. We obviously didn't spend a lot of time on this.
It's a thing of beauty, Jared.
So, yes. So we could obviously make this look nicer if we wanted to, but I think this is kind of another good example of kind of creating custom simulators using our platform.
You want to run that on the device? Whoa, get in frame, LED. There we go. I can't get that lovely shade of brown that you had on the simulator, unfortunately. But there you go. Same thing running over here on the real hardware. Very cool.
So that's pretty much the presentation. Hopefully we've given everyone kind of an idea about how this type of simulation can be useful for IoT development. Of course, we're constantly working on improving our tools to make simulation even better and more robust. We welcome any ideas or comments that you might have about this. We think this is a good idea. Maybe something that can be implemented in other IoT platforms. So if anyone has any questions, #virtual-IoT, we're happy to kind of take those questions now, whatever you have.
Indeed. And while we wait for the questions to come rolling in, I will say briefly that if you want to learn more about our platform, you can go to Canoma.com. You can pick up the Canoma Create from SparkFun, where we've been a top seller. You can download Canoma Studio, of course, for free at Canoma.com/studio. You can go to GitHub, search Canoma, and find our entire platform and all the sample code that's built on top of it. And then when you start playing around with this thing and you want to get involved in the community, go to forum.canoma.com and you can hang out with us there. You can also check in with us on social media, on Facebook, Twitter, Instagram, I hear is coming soon, very fancy. So check us out, where we do lots of meetups and conferences and hackathons and things like that. So, any questions?
Well, I do have a question. Can you maybe elaborate on how easy it is to develop your own simulator? Like, if I want to reuse existing JavaScript libraries, are there any constraints, anything I should be aware of?
Well, so Phil, it's relatively easy to create your own simulators. I kind of showed a few examples of that. There's a little bit that you need to learn about our framework, the Knoma.js framework, and how to construct UIs using our software. But for the most part, for just like importing other JavaScript libraries, we're compliant with JavaScript. We don't have support for some of the web. Some of this web-specific stuff, but as a pure JavaScript language, we'd be compliant with any kind of libraries out there.
Yeah, so often if you want to do kind of custom simulator design work, a quick and dirty way to get started is to use HTML5 Canvas, which we have full support for built into our platform. And so you can build up, you can grab whatever random like Canvas libraries you want out there in the world, and you just kind of strip out any place that talks about the DOM or browser or window and replace it with references to our Canvas objects, and then you can draw directly in there. And then when you get more serious about things, we also have much faster underlying implementations of kind of containment-based user interface hierarchies.
We also have a kind of a library of widgets for the simulators that you can use. So a lot of the widgets that I demonstrated here today, those can be reused in your own simulators if you want. So if like, you want to use the data generator, for example, from the analog input, you can grab those parts that you want to use in your own, or buttons, sliders, those types of things. We have libraries for that.
Okay. Another question is, do you expect the Knoma Create to be more than just a platform for simulating sensors and the like? Like, is there support for, if I want to do Ethernet communications or Wi-Fi communications, is this something that is part of the platform or that could be added to the platform?
Very much so. So Knoma.js is kind of a connected first platform. So the actual like JavaScript framework has built-in HTTP, HTTPS, MQTT, CoAP, kind of all the tools you need to connect multiple devices together and communicate between them. It's actually kind of very much a REST first platform where kind of every single handler, every function that you build an application out of is actually a web server in and of its own right. And so if you look at some of our tutorials at Knoma.com, actually, we have a lot of information about how you communicate between two devices. And then the device itself, the Knoma Create device here, actually has Wi-Fi built-in. We've suddenly picked up an echo. So it has Wi-Fi built in and is capable of doing a lot of that communication on its own. So all built into the system.
Okay, excellent. So I don't see more questions. Let me just have another look at Twitter very briefly. So yeah, I don't see any more questions. But please, if you are watching the replays on YouTube, feel free to comment on the video or add a comment on the meetup event, and we will make sure to. I mean, Jared and Andy will make sure to answer them. Thanks, guys. It was really very informative. So I guess again, people want to go to Knoma.com, right? If they want to learn more.
Yep.
And Facebook and Twitter, etc. And yeah, thanks for joining us. And I think our next meetup is gonna be on July the 2nd. It's not confirmed yet, but just monitor the meetup.com page, and you'll make sure to see when that exactly is. Thanks. Bye bye.